Alright, so this is the equipment we use. Let me now set up the theory for you. Here I have a picture of the equipment that I just used. A vibrating tuning fork of frequency F is held at the mouth of a long vertical tube that is filled with water, and water can be drained out of the tube by using this system, as I demonstrated this to you. As the length of the air column increases, as the water level falls, the length of the air column increases, the sound becomes louder, and at the point where the sound is the loudest, stop the water flow when the sound has the maximum loudness, and that is when the air column resonates with the frequency of the tuning fork. That means the fundamental frequency of this column of closed air will be equal to the frequency of the tuning fork. That is what it means at that time. Now this is where the first resonance occurs. Measure the length L1. So in the experiment you will measure that length L1 of the air column. In my experiment we got that as 16 centimeter. Alright, now this will be the mode of vibration at that time. There is an antinode and a node, an antinode at the mouth, a node at the closed end. Now actually in practice, an antinode does not form exactly at the mouth, but a little above the mouth. That means we need to apply a correction here. So let us say that the antinode is formed at a distance x from the mouth. That means if the length of the tube you measured is L1, then a quarter of a wavelength is actually L1 plus x. So we will say L1 plus x equal to lambda by 4. This is our first equation. When you get the first resonance, measure the length L1, and if the correction you have to apply for the antinode is x, then L1 plus x is a quarter of a wavelength. Now x is called the end correction, a correction we apply because the antinode is not exactly at the mouth but slightly above it, a distance x above the mouth. Now allow the water to fall again, just like I showed you, and stop the water flow when you hear the next loud sound. That means a longer length of air will now resonate with the frequency of the tuning fork. Now this will be the mode of vibration when you hear the second loud sound. That means the length L2 that you measure will now have an antinode, a node, an antinode, a node. This is the second mode of vibration. And in this case, you can see a quarter of a wavelength, plus a quarter of a wavelength, plus a quarter. There are 3/4 of a wavelength inside the tube. And what is that equal to? This L2 plus x. So measure the length L2 of the air column. We have now the equation L2 plus x is 3 lambda over 4. We have now two equations, L1 plus x equal to lambda by 4, L2 plus x equal to 3 lambda by 4. We can now use these two equations to obtain an equation for the speed of sound, the velocity of sound in air. Now x can be eliminated. Can you eliminate x from these two equations? Very simple. Subtract equation 1 from equation 2. So subtract equation 1 from equation 2 will be L2 minus L1 plus x minus x equal to 3 lambda by 4 minus lambda by 4. Is that right? So you get L2 minus L1, or L1 plus x minus L2 plus x equal to 3 lambda by 4 minus lambda by 4. Subtract the left hand side from the left hand side. and right hand side from the right hand side. What will this be now? You can see L2 minus L1 equal to, this plus x minus x will cancel. We get L2 minus L1 equal to lambda by 2. And therefore lambda equal to the wavelength of the wave inside the tube is 2 times L2 minus L1. Now this is something you measure, so you know the wavelength. Do you know the frequency? Yes, you know the frequency. The frequency is the frequency of the tuning fork. So you know the wavelength, you know the frequency. Can you find the wave speed, wave velocity? V equal to F lambda. That means V, the wave velocity, the velocity of sound in air, is 2F times L2 minus L1. And that is a very simple experiment that can be done to measure the speed of sound in air very accurately. In fact, you can get the answer within 0.5% of the actual value. Let's do an example. An organ pipe open at both ends has a fundamental frequency of 400 Hertz. If one end of this is now closed, what will be its fundamental frequency? Do you remember the equation for the fundamental frequency of an open tube? Open tube means open at both ends. The fundamental frequency of an open tube is V over 2L. Whereas the fundamental frequency of the air column in a closed tube will be V over 4L. Alright? This information is important for us. So what do we know? The fundamental frequency F0 is 400 Hertz for the open pipe. Now, velocity of sound in air is 340 meters per second. For an open pipe, the fundamental frequency is F0 is V over 2L. We know the value of V, we know the value of F0, therefore we can calculate the length of the tube from here. Alright? So length of the tube equal to V divided by 2F0. Alright? Use the values of V and F0. Or we can leave it like this because we are going to use this in the second part. What is the second part? This open tube is now made into a closed tube. That means one end of it is now closed. If one end of this now is closed, it now becomes a closed tube. Now, if the fundamental frequency of the closed tube is now F, do you remember the fundamental frequency of the closed tube? It will be F equal to V over 4L. And now, this L, the length of the tube hasn't changed, has it? It's the same tube. Only thing is, it was open in the beginning. We just closed one end. The length hasn't changed. So this length equal to this V over 2F0. So I'm going to replace this L by V over 2F0. That will be V divided by 4 times V over 2F0. Can you simplify that? Now, when you simplify this, the V and the V will cancel. 2 cancels with the 4, giving us a 2 on the denominator. This F0 will go up. So this will simplify as F0 over 2. The frequency of the closed tube, the fundamental frequency of the closed tube is half of the fundamental frequency of the corresponding open tube. That will be 400 Hertz divided by 2 equal to 200 Hertz. In other words, if the open tube, the air column inside the open tube will resonate with a tuning fork of 400 Hertz, if one end of it is closed, then the air column inside that tube will resonate with a frequency of 200 Hertz. That's the meaning there. All right, another one. The shortest pipes used in organs are about 7.5 centimeter. Tell me one more time, will the shortest pipe will give you the highest frequency or the lowest frequency? Well, if you know, an organ pipe, they're all open tubes. What is the frequency of air column in an open tube? V over 2L. L is on the denominator. That means as L increases, the frequency decreases. So shortest tubes will give you the highest frequency. Longest tubes will give you the lowest frequency. All right, so if you look on a church organ, you got tubes that are very small and tubes that are very long. Each will give you the corresponding frequency. So you have the church organ has a tube that is 7.5 centimeter long. What is the fundamental frequency of this pipe? Well, that's a very simple problem. The organ pipe is an open tube, open on both ends. What is the fundamental frequency of an open pipe? It will be V over 2L, and you know your length, and you know V, the speed of sound in air. What is that? 340 meter per second. Length of the tube is 0.075 meter. Remember to convert units to meters. The organ pipes are open at both ends, and therefore for an open pipe the fundamental frequency is F0 equal to V over 2L. V is 340, L is 0.075. So using those values, we get the fundamental frequency of that pipe is 2267 Hertz. You can see a short tube gives you a very high frequency.